Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hey y'all, welcome back to Physics with Beth and Beth. We're in AP Physics 1 curriculum still, where we will be we have 2 more units after this one, 7 and 8. We're in Unit 6, which is Energy and Momentum of Rotating Systems. We've already talked about that energy piece with rotational kinetic energy, and today we're going to introduce angular momentum. All right, just like we've always introduced these things in Unit 5 as well with angular, it's always nice to put it side by side with what we already know from first semester about linear. So we're going to compare this momentum, linear momentum, to angular. It just helps stick in your head and helps give you a better idea if you can compare it to something you've already mastered, because you are masters at that first semester material by now, I'm sure. So let's talk about, first of all, what is angular momentum? Well, when we talked about linear momentum, we talked about that mass times velocity that was coming at you. And in physics, we like to say that momentum is the real MVP, because it is mass times velocity equals that momentum. And we use P for that symbol for momentum. All right, so the real MVP. If you want to flip it, you could say P equals MV, same thing. But anyway, so that's what it is. In other words, we talked about in an earlier video in that was probably Unit 4. We talked about, like, if I had my 100-pound lab running at me at 5 meters per second, and then I had my little foo-foo daughter's dog, that's the cutest little long-haired Dachshund, running at me at 5 meters per second and maybe weighs 10 pounds, 15 pounds, the lab can actually have enough oomph to like knock me over, all right? That's that momentum, that mass times velocity. And the more mass you have, the more momentum, the more velocity you have, the more momentum. All right, well, with angular, we also, what is angular? Oh, and remember we talked about this momentum was a vector, all right? So let's not get sloppy with my arrows here. It's a vector. All right, well, angular momentum is a vector as well. So what is it? Okay, it's the same thing. It's a quantity that describes the rotational motion of an object. Momentum was a vector quantity that described the motion of an object moving in a line, linear. Now we're talking about a quantity that describes that motion with rotational motion. All right, so what it looks like, first of all, that's what it is. It is a vector, and just like with velocity had direction, west and south was negative, north and east was positive, up was positive, usually down was negative, usually. You can assign that different sometimes in a problem, but anyway, with angular momentum, we're going to remember that counterclockwise is positive and clockwise is negative, okay? Perfect. So let's talk about what angular momentum, we now know what it is. We now know it's a vector because it is going to have direction. And we're going to talk about the symbol. First of all, the symbol is going to be an L. Kind of crazy. And I've told you this before in these videos in Unit 5 and in Unit 6, and I'm going to tell you again. The more you can take just a few minutes extra and practice the units with the symbol, with the word, that's going to be so critical in being successful in Unit 5 and 6. Because you're going to have word problems and you're going to need to know that radians per second is angular velocity. Because those units are going to be your little clue. If you think of word problems as a little mystery, these are your clues. So knowing the symbol so you can look at your equation sheet and see what, oh, angular momentum's an L. Okay, they asked for angular momentum. I'm looking for an equation with an L. All right, or you know your units and you know what variables those plug into. So please spend some time with symbols, units, and the words, making sure you're firm on that. But an L is the symbol. A unit we're going to get to in just a minute after we look at the equation. The equation is going to be L equals, instead of mass, so instead of the momentum linear P, it's an L. Instead of mass, we're going to sub in that rotational inertia, or moment of inertia. So there's going to be an I here. And instead of linear velocity, we're going to sub in angular velocity. This is your equation for momentum for rigid objects. What do I mean by rigid objects? I mean cylinders, discs, hoops, spheres, hollow spheres, solid spheres, rods, anything that's like the rigid object, that is going to be the equation. So now let's take units. Okay, well, for moment of inertia, that was, if you remember, moment of inertia has different, there's some little fraction there, or 1 mr squared. So mass is a kilogram. R is measured in meters, so that's meters squared. And then that's I. Angular velocity was radians per second. So I'm going to divide by second. And you're like, yeah, but where did the radians go? Radians we consider a placeholder, so they don't actually go in the units. So we have a kilogram times a meter squared divided by a second. So the radian you wouldn't put here, that's a placeholder. All right, so that is now the unit. So now you know the unit and you know the equation. All right, so we're just going to get started really quickly and do a problem now that we know that. And that angular velocity, again, has direction. That's why this angular momentum is a vector. We're going to jump right in to our first problem. I have 2 problems on the board. We're going to get there. There's going to be one more equation you're going to need for angular momentum. This is for rigid objects. We're also going to have one for point masses. We'll talk about that in just a second, but let's just jump in really quickly. I have a rigid object here. I have a cylinder of radius 1.4 meters. It has a mass of 15 kilograms, and it's rotating at 2.7 radians per second. They want to know what's the magnitude of the cylinder's angular momentum, and then what if you replace it with a hoop. All right, so here we go. I'm going to erase this up here so I have a little bit more room, and we're just going to jump right into this problem. We know the equation is L equals moment of inertia or rotational inertia times our angular velocity. I'm going to identify some things here. I've got radius is 1.4 meters. Again, they told me the word in the units, so that was pretty confident. Mass, M, and it's in kilograms, so is 15 kilograms. Sorry about that. 15 kilograms. And then we have this, I know radians per second, that's angular velocity. I know that, and I know that's a lowercase omega because I'm going to spend some time getting familiar with those units and the symbols and the words because they just don't logically make sense in this unit. Okay, perfect. I've got all that. Now, I have a cylinder. I always ask my students to memorize 2 moment of inertias. For a cylinder, which is also a disc. Those mean exactly the same thing. If you see a disc or a cylinder, that's what that means, and that is 1/2 mr squared. And I asked them to memorize the hoop. The hoop is mr squared. All right, so it's twice as much moment of inertia as a disc. And if you recall from our earlier videos, what does that mean? It means the resistance to rotate. A disc has half the resistance to rotate. So if you put a disc and a hoop on a ramp and race them, the disc is like, shoot, yeah, let's roll. All right, but a hoop is like, nah, give me a second, then I'll go. All right, because it has more resistance to rotate. The higher the moment of inertia, the higher the resistance to rotate. All right, perfect. So I've got a cylinder, and I know that, so I'm putting 1/2 mr squared in here times my angular velocity. All right, well, now it's just plug and chug. We have everything. So it's 1/2, the mass is 15, the radius was 1.4, and it's squared. Do not forget square. It's easy to forget that. My angular velocity was 2.7. If you were to multiply all those numbers out, you would get 40 kilograms times meters squared over a second. All right? Now, if we want to look at this, don't forget that units are extremely important. If this ends up being in centimeters, you must convert to meters. If this is in grams, you must convert to kilograms. If this is in RPMs, for revolutions per minute, you must convert to radians per second. I kind of knew this video might be a little long, so I went ahead and just put it in the right, but don't forget to check your units, get them in the right spot. Now, they said, okay, what happens if it's a hoop? Okay, well, if it's a hoop, my moment of inertia is simply mr squared. The half goes away. All right, because for a hoop, I'm going to put a hoop here. Also tires, a lot of times they'll say tires, and you can consider it a hoop, is mr squared times my angular velocity. So because remember, each rigid object will have different moment of inertias. There's a different one for a hollow sphere versus a solid sphere versus a hoop versus a disc. So they will give you the moment of inertia formula if you need it, except for these two. I like my students to memorize these two. All right, but we have mr squared times my angular velocity, so it's going to be 15 times 1.4 squared times 2.7, and that's going to be double. That's going to have double the angular momentum of 80 kilograms times meters squared over a second. All right, perfect. That's exactly how you do it for rigid. Hopefully you've got this. I'm gonna erase it, pause it if you don't, because we've got to move on to a point mass. So we talked about point masses in other videos. Point masses is simply some object that we are reducing down to a point of a center of mass, okay? So what does a point mass look like for angular momentum? And this is really weird. All right, you're going to see this in collisions, because remember with linear, we had collisions where we were doing conservation of momentum. Well, the next 3 videos we're going to do after this one is we're going to do the conservation of angular momentum, and we will have collisions again, but these collisions will be with rotating around an axis. Okay, so this point mass, I'm going to do a little example here. I have my disc that will spin. All right. Now, if I have this disc that will spin, you can actually have angular momentum with an object that's moving in a straight line. And you're like, what? If it's moving in a straight line, how is it angular momentum? Because angular momentum is about rotating motion. Okay, look at this. And I like to do this in my classroom with a Nerf gun and a disc, and I hit the side of the disc with a Nerf gun, and it rotates. So if my finger is coming straight at this, it causes it to rotate around this axis. So even though my finger is moving in a straight line and interacts with this, it's moving linear, it actually has angular momentum in relationship to this axis of rotation, because it is at rest and now it's rotating. Something caused that to rotate, and it was my finger moving in a straight line. So it actually has angular momentum, my finger, and it would be the point mass in that. All right, so what does that formula look like? Oh, and also if you think about this as a merry-go-round, in the States we have the merry-go-rounds in our parks where they spin just like this. A student, maybe an elementary student, can run up, or primary, can run up and jump on this thing. And let me see if I can do this with this bunny. It didn't work well before, but we'll try it. So I have a little bunny, runs up and it jumps on this, and then this whole thing starts rotating. All right, well, it's rotating. It was at rest and it's rotating now because this little guy came at it with an angular momentum in relationship to this axis. Hopefully that makes sense. Because it seems weird that it's moving in a straight line, but this is what it looks like for a point mass. Well, what is a point mass again? It could be a kid jumping on a merry-go-round. It could be the little bunny jumping on something that spins. It could be a clay wheel, and you put a piece of clay as the wheel is spinning. All right, but those are all point masses. They're just something that's going to be landing on that rigid object. All right, the merry-go-round is a rigid object of a disc. All right, the potter's wheel, the clay wheel is a disc, and you have a piece of clay as the point mass. So the point mass is that object that's interacting with that rigid. And it's going to look like this, R, because it is in relationship to that axis of rotation. So wherever your point mass is in relationship to your axis of rotation, times your linear velocity, mass times velocity, which we said, hey, that is your linear piece. But now it's angular momentum, and that's going to be for a point mass. All right, so that's your formula. So now we're going to do a question on this, and we're going to say, hey, we've got a 60-kilogram child that runs at 5 meters per second at a stationary merry-go-round with a diameter of 3 meters. So the merry-go-round has a diameter of 3 meters. If the child is going to jump on the edge of that merry-go-round, what is the child's angular momentum right before jumping on? Even though, so we're going to draw this out from looking up above. So we're looking up like from a drone view. Here's my merry-go-round, and I have a child running straight at that edge at 5 meters per second, and that child weighs 60 kilograms. And that is my point mass. That's going to be my mass, and that's going to be my velocity of that point mass. All right, and we said that this thing was 3 meters in diameter, so its R value is 1.5, and that mass is going to land right there, that child, okay? Now they want to know, hey, right before it jumps on, what's its angular momentum? It's in a straight line, but it has an angular momentum because it's going to cause this merry-go-round to spin. So angular momentum in relationship to that point axis rotation. Here we go, easy peasy. And I'm actually going to erase all this because this is the other problem, so we can get that out of our way. We have RMV. We've already identified everything. It's plug and chug. 1.5, the mass is 60, and the velocity is 5. And that's going to become 450, oops, not a parenthesis, L equals, kilograms times meter squared over second. Yes, it's the same thing. This is a meter, this is velocity, meter per second. And then you have a mass of a kilogram and another meter. So that's kilogram times meter squared over a second. It's the same. All right. Now I ask you, okay, wait though. This child is not going to run at it on the edge anymore. This child is now going to run and jump on this thing at the halfway point, half R. Okay, so now how do I do it? What is that angular momentum? If they jump on halfway when they run and jump, they're not hitting the edge anymore. They're going to run and jump right there in the middle. Okay, well, it looks like this. It's just 1/2 R mv. So we have 1/2, mass was 60, velocity was 5 meters per second, and our angular velocity is 225. It'll be half. So what that R is the distance from the axis of rotation to where the point mass lands on your rigid object. So let's write that down. Where R is going to equal the distance from axis of rotation to where the point mass, and by the way, all of these were point masses. I should not have gotten sloppy about that. Where the point mass lands on the rigid object. And again, something moving in a line can have angular momentum if you're actually referring to it in relationship to a rotating object with an axis of rotation. Okay, perfect. That's it. We have 2 formulas now for angular momentum. One for point mass. Remember, point mass is going to be any object that lands on that rigid object that's going to cause rotation. All right, we also have an angular momentum for rigid objects. Now we are getting ready, the next video, which is fun. Those are fun problems. They are going to be collisions with these point masses with rigid objects that can rotate. So we're going to start doing a conservation of angular momentum with those collisions. So look forward to those. Hey, if you like this video, give us a thumbs up. If you want to subscribe, we would love to have you subscribe if you're enjoying these videos, or share with your peers to help them out if you feel like these videos are helping you. And we really appreciate you listening, and happy physicsing.